We're going to see another example in here. You have this bicycle that moves along a straight road such that the position is described by this graph that is shown in the figure 12.9a of the Hibbeler book. Construct the velocity versus time and the acceleration versus time graphs for t is between 0 and 30 seconds. So we have in here the combination of two motions. Remember, the idea of calling it erratic motion is not because it's sort of lost out there. No. It is because the motion is composed of two different parts, and the motion is composed of two different functions. That's why. So this is important in our basic review because we want to make sure that when we analyze an accident, we look at all the evidence and there might be different kind of motions at different times as time goes on. Okay, like for example, a vehicle may crash with another and have a direction of the velocity, but after the collision, it will go backwards, for example, which happens a lot. And so you have to have the ability to make these plots and make the correct calculations that we would like to do when we do accident reconstruction is to obtain the different velocities and accelerations at different points. Velocities are important because we want to know at what velocity did the accident occur, for example. So this is why we're doing this review of dynamics, and hopefully with these exercises everything is clear. So in this case you have this bicycle that is moving in the straight road, such as is the position described by the graph shown in this figure. In the first 10 seconds you have a parabola, basically, that the position is t squared, and right after you have a straight line which indicates that it has a slope constant. Yeah. So what's the solution? Since the velocity is ds dt, the velocity diagram can be determined by the differentiating the equation defining the st graph, which this would be sx would be t squared and the velocity would be 2t between 10 seconds and 30 seconds. The position is 20t minus 100, and then you have that the velocity is ds dt. Take the derivative of this equation and you got it. Okay. Let's take a look at this other example also. Here we have a vehicle, a car, test car, starts from rest and travels along a straight track such that it accelerates at a constant rate of 10 for 10 seconds and then decelerate at a constant rate. This obviously is the situation where you have a test for finding out the friction between, the coefficient of friction between the ground and the vehicle. You have the graph B of t. In this case, the question is, we want to draw the VT diagram and the ST diagrams and determine the time T prime needed to stop the car and how far has the car traveled. That's a pretty good question. All right. So let's examine this. You have a time versus acceleration here. So it accelerates, obviously this is a value and then decelerates also with a negative value. So this would be, excuse me, the acceleration diagram. So because the velocity is, or you say, the acceleration is dv dt, it follows that the velocity is a dt. The vt graph is determined by integrating the straight line segments of the AT diagram using the initial condition that v is 0 at t0 we have, or between 0 and 10 seconds. So the acceleration is 10. If you integrate both sides, you're gonna get the b is equal to acceleration times time. So in this case would be 10s and b would be 10, which would be the acceleration times time, minus 100 meters per second, using this as the initial conditions for the next time period. So in this case, the acceleration is going to be minus 2, and then the integral of 100 to s ds, and then the velocity is going to be minus 2t plus 120. So when t is equal to t prime, we require that the velocity is 0. So t would have to be from the picture 12b, which is in here. It would be the velocity. Yeah, this would be at 16 here. So you write the equations here. Okay, so this would be that the area under the AT curve is equal to the change in the car's velocity. So we require that the change of velocity is 0 at A1 and A2. So you have 60 seconds in there. Same way. Anybody has some question? No, this is of course the other graph that we were talking about. The ST graph is the position versus time. So ds is dv dt. So in this case, if we know the velocity diagram, we should be able to know the position diagram because we can integrate. So you see the velocity is v times 10t. So if you integrate both of these, you have that the position is 5t squared. So when t is 10 seconds, this is 500 meters using the initial condition. We'll use on the next one. 10 seconds between 10 and 60. B is minus 2t times plus 120. And in this other one, you have the integration of that equation is going to give us the position. And that's what we see here. See? So the ST graph is shown here. Okay, here's just a note that you can actually do you can obtain S when t prime is 60 seconds because of the triangular area under the curve, and it will yield the displacement 60 seconds t. So delta S would be 1/2 of 60 times 100, 3,000 meters.